So good afternoon to you all, and it's a great pleasure to be here talking to you about my journey in archaeometallurgy. And as is the nature of the series of Women in Physics talks, I think I should begin by telling you a little about my motivation and background and so on. And so archaeometallurgy is typically to do with the study of ancient mining and metallurgy. And up there you see this old copper working in Agni-Gundala, which is in Andhra Pradesh, and that was me in 1992. At that time I was a doctoral student of the Institute of Archaeology in London. But before that I had done a BTech in engineering physics from IIT Bombay. And you can see that greenish malachite stain of the old working because copper, of course, is found as an ore, which is a green malachite ore, and you might have even used it in ornaments and things like that. And that's what you're seeing there, the ore working with load, which has been worked out like this in antiquity. And actually, to tell you, just to get you a sense of how it is quite an adventurous profession to be in archaeology and archaeometallurgy. And then when we went to another old working, which was a little further here, this is a place close to Guntur, I heard this rustling sound and turned like this. And of course, I was with somebody from Hindustan Zinc in those days who was accompanying me. And so we heard this rustling sound, and I thought it was must be a rabbit or something. And it was, I first thought it must be a leopard because it was obviously a feline, and it had it seemed to be, spots. But then when I looked closer, it bounded so fast, like across the hill face, just like that. It was gone in a flash. And then I said, no, was that a cheetah? Because it had, the rings really, because the cheetah is known to have been there in this part of Guntur district, but it had actually gone extinct. And then that man from Hindustan Zinc, he said, yes, ma'am, you're right. It was not a leopard, it's a cheetah. And it's probably one of the rare cubs which was there in that area. So just to give an idea, of how exciting it is to be in archaeology. So we have a sense of adventure, which I did, although of course I was also doing physics and so on. So this seems to be the kind of area that I wanted to get into, and to give you a continuing feeling of, the adventurous things that one gets up to. So this is actually the site in Adichanallur in Tamil Nadu, and this is an urn burial site where you have these very large terracotta urns, and at the bottom of the urns, of course, it's a secondary burials, but you also find a lot of iron implements and so on. So what we were also trying to do was to take with us a portable XRF machine to go down and do some analysis of the artifacts and all that. And this field trip I made not long after a total hip replacement that I had for this ongoing condition of bilateral developmental hip dysplasia, which affects only women, by the way. But also, of course, to point out that as women, as you know, we face various challenges being in science or being in archaeology, which involves remote travel. So I hope that this talk is also something which I suppose as established women professionals, we also need to mentor, inspire, and encourage the next generation and so on. So here, of course, as I was mentioning, archaeometallurgy is to do with the scientific study and documentation of metal artifacts for the study of the history of technology of mining and metallurgy in antiquity. And as I said, I had a background in engineering physics, and somewhere along the line, I felt that since I was interested in, also looking at monuments and heritage, and I had, artistic interests as well, I didn't just want to be doing only what I was doing at that time, which was quantum mechanics and, studying superconductors, which I found that interesting, of course. But so what I was studying was not totally out of place and irrelevant also, because there was a lot of exposure we had to spectrochemical analysis and so on, which is now a major part of the kind of work that I do, because it's really materials characterization of ancient artifacts and metallurgical heritage and so on. And so, of course, it is quite inspiring when one is recognized, and this is me with Dr. Balram from Indian Institute of Science when I got the Kalpana Chawla award for the women scientists and so on. And here, of course, this is another site that I've been also working with, which is Kiradi, which is near Madurai, which has been now carbon dated to about 600 BC, and we're looking at some remnants of paved bricks and so on. Um, so, and of course, reflecting on my journey, this was me in another lifetime in the 90s. I was also a postdoc after my PhD work at the Institute of Archaeology in London at the Department of Conservation in the Freer Gallery of Art. And here you also see, for example, the using of the X-ray fluorescence machine and so on. And of course, I have to say I've been very grateful for all the support that I've had from my family. My father, Dr. Srinivasan, who's a former Atomic Energy Commission chairman, and my mother, also a very adventurous lady who was with the Nilgiri Wildlife Association, and these are in fact some of her photographs here. And of course, my husband, Digvijay, has been a big support, and daughter who's tolerated all of this. And of course, I should also say that since we are talking about physics, definitely I was very influenced by my father when I was a child, particularly because he was working with setting up various nuclear power plants. And in fact, the Asian scientists had listed him as the chief architect of India's nuclear power program, since he'd been involved with setting up 14 nuclear power plants and so on. And and in fact, when I was very young, he used to describe the processes of nuclear fission and chain reaction of the uranium-thorium cycle to generate atomic energy. And I used to visit a lot of plant sites and, seeing the Cherenkov radiation and the making of the calandrias and so on. And of course, he was also very involved with the push for self-sufficiency in the Indian nuclear program after the nuclear tests in the 70s, when some of the earlier support that was there from Canada and so on was withdrawn, and for making calandria completely from Indian technologies and so on. So he's talked quite a lot about all of that, and in terms of this whole thing of the push for self-sufficiency and so on. And my mother also was a very big influence. As I said, she was also chairperson of World Wildlife Fund. And this was a pilgrimage, a photograph that I took back in 1987. And that also tells you where, of course, a connection with art and culture and intangible heritage started coming in my life. And I made this trek, which was also a trek pilgrimage to Amarnath, which was snowbound at 14,000 feet, very adventurous. And of course, I should also say there was also the fact of, her grandfather was Sir C.P. Ramaswamy Iyer, who was a Diwan of Travancore and also a great reformer and lawyer, and contributed a lot of scientific infrastructure, also the Travancore Observatory and Paikara Dam, and of course, more famously, the Temple Entry Act, which allowed the access to temples to all communities and classes. In fact, he was one of the first people to pioneer the Temple Entry Act, and for opening out to all castes and creeds and so on. So a great reformer for both for women and communities and such like. So that was the baggage, I guess, to for me. And of course, I was very interested in art and cultural heritage. And I should also mention that when we talk about women in physics, it's also good to draw inspiration from, I know there is this stereotypical sense, of course, like in all societies, feudal societies, Indian women also face a lot of patriarchy and so on. But when we look at our art and cultural heritage, there is a lot of inspiration that can be gathered from that too. And particularly, of course, today we see, of course, in South India, there's a lot of women. In fact, my aunts also in Bangalore were teaching physics and mathematics in their time. So a lot of women had got into sciences, particularly, say, in Madras and Chennai and all that, and now much more in so there was more of that in the South, but now also in other parts of India. But looking at our cultural heritage, we have these rather inspiring depictions. This is a very beautiful sculpture of Saraswati, the goddess of learning, in the Brihadishwara temple in Tanjore, circa 1010 CE. And here also, 11th century sculpture of the Kalyana Chalukyas shows the Jalasangvi, which is basically a woman who's actually, making a copper plate inscription over here. So it also gives you a sense that, of course, in the Hindu context, there were restrictions that the women were not at all times able to access the learning of the Vedas and so on, apart from other castes and communities. But here you can clearly see that there is this woman who's writing in Hale Kannada and so on in the copper plate inscriptions. So I think it's a lot more of a diverse picture than any one kind of stereotype in that sense. And here there's also a beautiful bronze icon of the Jain goddess Ambika, which is also inscribed to the 10th century. And here you see that, she's also holding a manuscript in the hand here. So again, this notion of, the female and, knowledge associated with the females. And here is also a very fine sculpture, a bronze sculpture from Tamil Nadu of Tamil poetess and saint Karaikal Ammayar, who is actually thought to have lived in the 6th century. And she came from the town of Karaikal, which is somewhere on the coast of Tamil Nadu. And there is a lot of devotional poetry and all that, which is attributed to her. And of course, she sings in praise of the Lord Shiva. And she was one of the Bhakti saints. So she didn't come from, I think she came from a merchant community and so on. So and she also prayed, of course, that's more of a myth, that she prayed to the Lord Shiva to become a hag, which is why she's depicted in this hag-like form. But of course, she plays the cymbals and so on. So in a way, it's a kind of, although we see a lot of very beautiful depictions of the feminine, it's also in a way a celebration that you don't have to always be beautiful to be venerated or something. You can also be, something which is, all kinds of forms are also, worthy of veneration in that sense. That's what I see in that depiction of Karaikal Ammayar. And of course, she also sings of Shiva's dance with fire and so on, which I'll come to. But I'd also done analysis of this bronze, which showed that it had about 20% lead and 3% tin. It's a copper alloy image, and I'll come to all that later. And this very spectacular image that you see here, which is a Chola bronze of the 10th century, is in the Freer Gallery of Art now. And this is thought to represent, at least some art historians believe, that it represents actually the deified bronze of the widowed Chola queen Sembian Mahadevi. And I don't know if any of you were following the Ponniyin Selvan series, and which had been also made into movies by Mani Ratnam. And so Sembian Mahadevi does appear as one of the characters in Ponniyin Selvan, because she was the great aunt of Rajaraja Choran, who's associated with the building of the spectacular Brihadishwara temple and so on. But what is quite interesting is that there's a lot of, this is just to show that women also had agency in the past. They were not just being depicted only, but she was, inscriptions suggest that she was a great patroness. And there is also a commemorative plaque at the Uma Maheshwara temple, which was dedicated to her late husband, Gandharaditya Chola. So it was actually, we know of the Taj Mahal, which was dedicated to Mumtaz Mahal, but here she had a temple also, which she built and dedicated to Gandharaditya Chola, many of them, because Gandharaditya was also a devotee of Shiva and sort of fasted to death. And this is a kind of plaque of Gandharaditya worshipping the lingam here. And it's also interesting that she's depicted, and there's also a town in Tamil Nadu named after Sembian Mahadevi, which is still called Sembian Mahadevi. So that shows the, and according to inscription, images of her were cast and also taken around in religious procession, which is probably what this image was intended to do. And it was Ananda Kumaraswamy who suggested that this may be one of the images of Sembian Mahadevi, which was taken around in procession. And you'll see that in the Tamil context, even the women, the deities, and the queens are also depicted with the Yajnopavita or the Punal or whatever, the sacred thread, which also shows that women also were associated with esoteric learning. It was not something which was only seen as a preserve of the male Brahmins. But I have to say, I haven't seen that much in North Indian descriptions. It seems to be very typical of the Tamil description of, Saraswati, and all. It always has the Yajnopavita and so on. Now, those bronzes were made by a process of casting, which is an age-old technology, and you all would be very familiar with the Mohenjo-daro dancing girl of 2500 BC, which is the earliest known cast figurine from the Indian subcontinent. And this is made by the process of lost wax casting. And typically in the lost wax casting, what is done is first a wax model is carved of the icon to be made. And here you see from the rear this wax model having been carved. And then it is invested with numerous layers of clay, going from the finest grade of clay to the coarsest layer of clay. And here, what is important is a lot of these bronzes were made on the banks of the Kaveri River. This is Swamimalai, which is just near the Kaveri. So it's really the alluvial clays of the Kaveri which are used to make the mold. And then once the mold has been made, the whole idea of the lost wax process is that when you heat the mold, the wax get expelled. And inside the mold, you get a hollow exactly in the shape of the image to be cast. And here you see the wax has been expelled from this mold. And then the metal is heated, and then the molten metal is poured inside the mold so that it takes the shape of this hollow which has been left from the wax being melted out. And then that is broken open, and final finishing and so on is done in the casting to yield the final finished image. And now I had also done microstructural analysis. I don't know how many of you here have a background in metallurgy, but quite simply, the microstructure refers to a small sample of the metal artifact being taken and then being polished and mounted and observed here under an optical microscope, but then you can also look at it under scanning electron microscopy and so on. So this is in fact a sample of a chola bronze which I had examined under the microscope. And as you can see here, it's a very typical structure which gives away what the composition is, which is basically a low leaded tin bronze. And you see these typical dendrites, which are formed from the as-cast process, these fern-like structures, which we call dendrites. And in the interdendritic space, you also see some of these blackish patches, which is because if you just take copper and add tin to copper, one of the problems is that there are some problems in casting it because of the freezing range and so on. But the addition of lead, because lead is a kind of soft material which flows into the grain boundaries and all that quite easily. It's a low melting metal and so on. So the lead sort of fills up these crevices, and so you get a better casting. So that's why rather than just using pure copper also, which also has some problems with casting, or just bronze and, which is just basically tin and copper. So they were also adding some lead to get a better casting. So this is what we called low leaded tin bronze. And of course, what is also interesting is that you also have these accounts of various in the scriptures and the Shilpa Shastras and so on, which describe some of these processes. For instance, the 12th century Deccan Chalukyan king Someshwara had a Sanskrit treatise known as the Manasollasa, which describes this process of lost wax casting, which in Sanskrit it was known as Madhu Chaiste Vidhana. And so basically that Madhu Chaiste Vidhana literally refers to the lost wax process. And they also describe again the use of 3 layers of clay and so on. So these were kind of some prescriptions which were also being followed over time. And it's also very interesting that you also get some, I mean, as I said, I'm trying to highlight as much as possible the women, who may have made contributions in various ways. And so you have the Tamil poetess Andal, who describes the lost wax process in a very metaphoric way. And of course, she says, "Ullai ulla meligu urukki vengalam ootra vali seydu pol," where basically she's talking about the ullai or the hearth into which, and she's comparing it to the clouds, and she's saying that she's beseeching the clouds to rain down on the Lord Venkatam who she worships, because of course this is the bhakti tradition where it's a very personal sort of relationship with the deity. So she's beseeching the clouds to rain down on the Lord Vishnu who she worships, and she's comparing that to the mold being heated and the wax being expelled out. So it's interesting that some of these nuances also had these metaphorical cadences. They were not just seen as just processes in their own right, but they also were seen in this kind of aspect of ritual and other aspects. And in fact, the hearth is also described as the karu, which is basically a comparison with the womb, because it's like the birthing process of the deity and so on. And so, of course, a lot of the practitioners of the metalworking and so on these days are men, but you also see a lot of women engaging in several aspects of the metal crafts, especially maybe not so much in the mainstream things like the making of religious icons and all, where maybe it's still the male sthapatis and all who hold sway, but in some of the maybe the crafts which are more of a utilitarian nature and all that, you do find there are actually a lot of women also working in the workshops. For instance, this is in Kerala. And here, what is being done is, what you see here is what I don't know if many of you have been to Kerala, you'd have seen these very big cauldrons, which they call the urli, which is also used for temple feasts and so on. And these huge cauldrons are still being made, for example, in Mannar and Irinjala Kuda and so on. And here you see again the wax model, which has been made. And it was actually also, the wax model is also built up by using hand lathes. So you see this axle here, and the mold is on that, and then it's all sort of turned on a hand lathe and really smooth, so you get that very smooth finish. And here, of course, you also see that it's quite interesting that the final grade of wax is terribly important for a good finish. And here, they were also using materials like, of course, cow dung and lamp black. And the idea being lamp black, of course, the idea of that being that it is very carbonaceous and carbon rich. And in fact, I also showed this at a workshop and masterclass that I was giving, coinciding with the carbon exhibition of the Science Gallery, which I don't know if you all have had time to go and see, please, but do go and see it. And this addition of lamp black on the surface of the wax, the last layer, is very important, because when the mold is heated and so on, this becomes a very adsorbent layer, carbon-rich layer, so it can absorb all the gases right out of the mold. Because if you don't absorb the gases out of the mold, it will actually give a very bad surface, and so you have to do much more finishing and so on. So there's a lot of little nuances where even using just organic materials, you're getting a very good casting. And here you also see this, of course, this was me there some years ago. Many of these processes, unfortunately, are dying out, but still, anyway, we have to document what we can. And so you here see this huge big furnace, which is used for dewaxing the mold and also for preheating, because that's also an important step that, once you have dewaxed the mold, got rid of the wax, before you pour the metal in, you must do the preheating so that the mold and the crucible is at about the same temperature, so that when you pour the metal in, you don't get a sort of explosion because of the fact that the mold can crack and so on. So there are a lot of nuances there which you find that they are dealing with using fairly simple techniques and so on, which have some kind of legacy here in terms of tradition. And coming back to the idea of women patrons, and since I'm talking about mining and metallurgy also, which is also a case of excavating, underground excavation, we have this very remarkable example of the Rani Ki Vav step well, which is attributed to the 11th century Solanki queen in Gujarat, which has also been declared as a World Heritage Site. And it's a very spectacular step well going right down. And we had also tried to do a kind of digital 3D printing and so on of the stepwell, which was done by undertaking laser scanning of the entire monument. That was a project that I was involved with, the India Digital Heritage Project. So we had scanned the entire monument, as I said, by laser scanning, and then generated a 3D point cloud, and then taken a 3D print so that you can see all the nuances and such like. And of course, here too, you see that the deity that is there is Vishnu Seshashayi, who's sleeping here on the snake Shesha. And there also you see, it's quite interesting that the Solankis basically were an offshoot of the Chalukyas of Karnataka. If you all have been to Badami and Aihole, again, this is actually a sculpture from Badami, which is now in the CSVMS museum. So this influence of North Karnataka, you also see going up into Gujarat and so on. And of course, there are very other famous examples of women as patrons. For instance, this is the Mughal era Itmat-ud-Dawla, which is in Agra, which is built by Noor Jahan for her father. And another very celebrated example, I don't know if you all have time, but if you all go to Belur and Halebid, it's just a day trip. You see this beautiful Hoysala Belur temple where you see this 13th century sculpture. And this is again thought to have been patronized by the Queen Shantala Devi, who was also a dancer. And of course, I did have a life also as a Bharatanatyam dancer, so that's why I put it in here. And also to draw attention to this, which I will talk about now in terms of the making of metal mirrors, because you see she's holding here a mirror and gazing at it, the Apsara or the Madanika, looking at the mirror and so on, which is another very favorite theme of Indian temple sculpture and so on. And in Kerala, we have a very exotic metalworking technique, which this is not a glass mirror, but this is actually a metallic mirror. So this is one of the aspects of archaeometallurgy. How do we try and understand how these artifacts were made? Now, when we look at the copper tin phase diagram, basically the phase diagram typically consists of, it shows you what happens when you alloy one metal to another metal, in this case copper, and then you keep adding tin to copper, and what happens at different temperature ranges. So as I was mentioning, the earlier sample that I showed you was of a leaded bronze, and there the tin content would have been typically less than about 15% tin, because that is when the alpha solid solution of copper in tin forms, as you see here, this symbol alpha. But so up to about 15%, the tin is actually soluble in copper, so it forms a solid solution. But what happens when you keep adding tin to copper? It actually becomes more and more brittle at higher temperatures of tin. And so, I mean, at higher concentrations of tin, sorry. So in fact, you find that in normal conditions, you don't really find too many heightened bronzes being used in antiquity because of this fact that as you keep adding more and more tin to copper, it becomes more and more embrittled. But it's quite interesting that in this traditional making of metal mirrors, they were very consciously aiming for a particular composition of tin in bronze at around, say, 32 to 33% tin, where what happens is that there is a predominant formation of this delta phase. And what happens here at this composition is that the bronze consists predominantly of this intermetallic compound, which is delta, which is a fixed which is a compound of a fixed composition of about of about this 32.6% tin composition. And what is interesting also is that this delta is a very silvery white and hard compound, and that's why when it's polished it takes a very good mirror finish. But it's also something which is formed at a very narrow composition range under usual casting conditions. So when we actually looked at the microstructure of a small piece of that mirror, and as you can see, it's practically as good as a modern metal mirror. And here you can see that the structure shows, you see the silvery white delta phase and a very fine network of the alpha plus delta eutectoid, because there's a little bit of alpha plus delta eutectoid also, which carries over into the, this is really where the alpha plus delta eutectoid range is. And this is what actually embrittles the bronze. So typically this should be very brittle and not very easy to cast. So where the genius comes in is that they actually try and use a very skilled technique to cast this delta bronze in a way that minimizes the brittleness and maximizes the presence of the delta phase. And then because it's a very hard compound of about 500 VPN, it can take a very good polish to give a metal mirror finish. So here typically you're seeing a traditional crucible cum mold, which is used to cast this delta blank. And this is a two-piece mold here and a very narrow space here, which is so that a very thin blank is cast so that the heterogeneities are limited, so you get a very homogeneous casting. And why I call it a crucible cum mold is that on top of this crucible cup, this is where the metal to be cast is placed. And then the whole thing is closed so that you get a closed crucible cum mold. And then we see the casting. And now you also see that this is a slightly different process from what you saw with the casting of the icons, which was an open casting, where you just pour the metal into an open sprue. But the reason why they were making a closed crucible cum mold here is that this helped to minimize the oxidation of the metal, because when it's open to air, then you get, even as you're pouring the metal in, you get oxidation, and that actually causes a very bad surface and all that, the fire skin which forms and so on. So this was to basically prevent the oxidation losses and so on, that they were using deliberately a closed crucible cum mold. Here was a metal placed, and then it's all sealed and covered. And as I was telling you, this alloy is actually quite brittle, this 32.6% tin bronze alloy. And here you can see how he's just broken it up by a hammer, and then this was packed here and covered. And then it's heated face down. And this was me actually in the 90s, actually trying my hand at the bellows and so on. Of course, nowadays they're using electric bellows, but earlier they would have used bag bellows and so on. And this is the late Janardhan Achari, who's no more, but his wife and family and so on are still taking over the practice. And as you can see, so this part which had the metal is heated face down, and this part would have had that very thin gap into which the metal would have been cast. And we also use various other techniques. This is a thermal camera here. So this is quite useful to understand what is happening in terms of the temperatures and so on in the foundries. You can see the color coding here. So what it actually tells you is that there's a huge difference of temperature between the top of this crucible cum mold where the metal has been heated to the bottom of the mold where it has actually been cast. And it's a very drastic drop actually in temperature of about, at least 300 or so, 300 to 400 degrees Celsius. So that also helps in I won't say it is totally like chill casting, but there is an analogy in terms of, it's almost like chill casting. So that actually results in a more homogeneous blank being cast. And then the next process, of course, is the polishing of that blank. And you're seeing here that after it's cast, it actually looks like that. Sometimes it can have some defects and so on. Then it's mounted onto this wooden polishing mold. And it is lapped here for several days back and forth. I don't know if you all have worked with metallographic polishing, but basically you would remember the rule that you all go first, get all the scratches to go in one direction, and then you look at it under the microscope. When it's all in one direction, then you go the other direction. So they do something similar like that, though of course they, are able to observe it, just by watching and so on, by visual observation, maybe because these are very large crystals we're talking about. And so you can see here, this, and the other interesting aspect is that this is basically a point image, because a modern mirror is made by, you use a mercury coating and then you have a thin layer of glass. So actually it's not a point image as you would know from your physics classes. There's a slight bit of refraction through glass which happens, but here you're actually able to get a very accurate pointing image. And I think it's also that you're getting reflectance across the spectrum here. And of course, you might say in antiquity, what other options would they have had to use for making a mirror? Well, they could have used silver, because of course, silver also has very good reflectance. But silver is actually very soft, and so it doesn't take such a good polish, and it'll start warping. And then I don't know if you've seen sometimes in silver mirrors, you can get very warped and funny faces and so on. So that was why, in a way, this was the ideal mirror making alloy that you could find for making mirrors. And this was one of the very large mirrors that was made by Janardhan Achari some years ago. And the other interesting aspect is, even as they polish it, they use the same powdered alloy for self-polishing, so that it goes and fills up all these defects. So you get a very good surface. So there are very little, little nuances that you can think of. And what was also interesting is, when I had shown that Belur sculpture, it's almost as if, this kind of wooden handle with the blank was being, used here as a mirror and so on. So we can speculate that this kind of mirror does have some kind of antiquity. And that's also interesting in terms of when we try to attach a geographical indicator patent to show that this was a kind of traditional knowledge, to look at the antiquity of the craft. Now, of course, if you think of what was happening in the Western world, there's a lot more of advances, no doubt, because in fact, the speculum metal was already being used in the, mid 18th century. Not exactly of the same composition as the Aranmula mirror, but certainly, bronze of a higher tin content, probably going towards 30%, but that would have also had some amount of arsenic and silver and lead, which was actually being used to make mirrors for telescopes. And I have also been to the house in Bath of the German-British astronomer William Herschel, who discovered the planet Uranus in 1781. And he had his own hand polishing unit here, as you see in the Herschel Museum, and then his telescopes and so on. And of course, you do have other mirror making traditions. For instance, the Chinese also made a lot of mirrors right from the early historic period, the Han Dynasty and so on. But that had a very different composition where they had a lot of lead also added, as I said, to make the mirror more castable. But the lead actually, as you know, it's a very black and opaque material. So lead would not have actually increased the reflectivity of the mirror. So in that sense, the Aranmula mirror is probably the best kind of mirror that you can make. Though of course it probably does tarnish. But presumably if you put it in outer space where there is no atmosphere, it would probably give the best mirror reflectance and could be used for some purpose there. And so it also made some analysis of old bronze mirrors. And this was actually an old mirror with the insignia of Travancore from Kerala with the Gadda Berunda motif. Because one thing I should say, that one problem we face in India is we're just not looking after our heritage very well. So many of our old, patrams and this and that, which you might be with your grandmother and this and that, they're all just being sent for scrap. Nobody's documenting all this, but if we did, I think it would be very important in terms of history and science, history of science and technology, to also establish, the antiquity of practices in our tradition. So I was telling you about that, the recent mirror, which had, quite a bit of the delta, with the alpha plus delta eutectoid as well, with the delta phase. But when I looked at this microstructure of this old mirror, which I think it is about 17th, 18th century, it's almost pure delta phase. There's absolutely very, very little traces of alpha plus delta eutectoid. So how did they actually, using those very traditional techniques, almost generate pure delta phase, which is actually quite difficult to do even in laboratory conditions. So it can tell you that the skills also in antiquity of handcrafting and all that were quite considerable. And of course, we do have some examples of mirrors in antiquity, going back to to the Egyptian world and so on. And also from the pre-Harappan context, from Quetta in Pakistan, in Baluchistan actually. But those compositions, we don't think I don't think it's been analyzed, but there's not much evidence that they were using very high tin bronzes in the Harappan period. It was more of low tin and so on. But still, we can get a sense of how that mirror was probably cast in a very thin blank and so on. But we do have an analysis that Breeks reported nearer here in the Nilgiris, which is the hill range that you have between Karnataka and Tamil Nadu. And in the cairns, in a 19th century report by Breeks, who was one of the collectors of the Nilgiris, British collectors, he had actually found a mirror example, which is now in the British Museum. And this was found to have 30% tin. So it's much more in the line of the composition of these bronze mirrors that we're talking about. So it's quite possible that such bronze mirrors were being made quite early. And these are, of course, not very well dated because they were not very systematically excavated, but it's thought to belong to the Iron Age early historic periods. So at least about the early centuries CE. And speaking of the Nilgiris, because that's also been one of the regions which I've been working a lot in terms of archaeometallurgy, and my husband is also from the Nilgiris, Digvijay. And here we are seen at one of the munds of the local Toda community, who have a pastoral community, who have their own distinctive practices and so on. And they're, of course, known for these very beautiful shawls which are embroidered in the Putkuli. And here you're seeing one of the Dogles, the Toda temples and so on. So all of us are around here with my brother and a daughter as well. And you can also see that, they live in the midst of these cairns. And I was talking about Breeks, who had unearthed some of these cairns. And what is quite fascinating is some of the material culture from these cairns. It's divided between the British Museum and the Government Museum, Chennai, which had been unearthed by Breeks and Elliott and so on in the 19th century. And there were also some very beautiful ornaments of gold which are found there, like this gold earring or a motif with a floral motif. And these are also quite interesting because these are some of the very early examples of gold which have been unearthed from the Indian subcontinent. I mean, when we look at some of the early sculptures from around India, we can tell that they were using, very beautiful ornaments, but many of them haven't survived because, of course, metal can be remelted, and particularly gold as heirloom is always being remelted and so on. So there are very few finds of archaeological gold, But this is a very interesting and early example of gold from the Nilgiri cairns. And it's also made using this technique of granulation, where these tiny, tiny spherules of gold are kind of added, which is because when you cut a foil of gold and you heat it, just by the surface tension itself, it tends to form these kind of little spherules, which is known as a granulation technique. So of course, one question arose then that, where are these artifacts made? Where are these gold artifacts made and so on? Or where have they come from? But it's interesting that right in the Nilgiris, you do have evidence of old gold working. There are some auriferous gold deposits there, where basically gold, of course, is a noble metal. So it is it is found in the native state as native gold. But, it's found dispersed amongst these quartz veins. So you can see here all the quartz veins. So these are these hard rock veins. So of course, then there was some ore crushing, and then the gold was, sieved in the water, and the particles are collected and so on. So that's how, so you see some very extensive old workings there. This is this mine which is going right down and so on. And as I was talking about those stone circles, these are really the kinds of stone circles you see there in the Nilgiris, the cairns, as I was talking about. And it's also interesting that more recent excavations are also helping to better date some of these early artifacts. And for example, this is a site called Shivagalai, which is an Iron Age site, which is an urn burial site also in Tamil Nadu near the Porunai River, which has been recently excavated by the Tamil Nadu State Department of Archaeology. And they had also sent some paddy from the urns to Beta Analytics for AMS dating, which is a kind of dating techniques, and which again uses accelerator mass spectroscopy and dating for the radiocarbon. And it was found to be dated to about 1125 BC. So that's very early, because again, we are finding early example of gold from Shivagalai. And we had done this portable XRF analysis. So X-ray fluorescence analysis, as you may all know, deals with the emission of characteristic secondary fluorescent X-rays from a material that has been excited by being bombarded with high energy X-rays or even gamma rays. And so this phenomenon is widely used for elemental analysis and chemical analysis, especially for metals and now also other kinds of materials. So you see here we had a portable XRF machine, which is very useful because we can take it to field sites and do the analysis right there. And of course, it's very nice when we can analyze gold, the best material to analyze, because gold is totally uncorroded. And of course, XRF is a surface analytical technique. So it only analyzes the surface. It's a very thin film of the surface it analyzes. It doesn't do a bulk analysis of the entire artifact. But what is useful is that in the case of gold, because it is uncorroded, you get a good analysis, which all adds up to 100%. And you see here, it's very high purity gold, about 87%. And there's some silver also, 8% or so, more in the range of electrum in a way. But it's, interesting that we now have these techniques to do the analysis. Of course, coming back to the studies on the Chola bronzes, because that was what a lot of my PhD thesis work was on, the compositional analysis of Chola bronzes. And also to talk about, again, the symbolic and the metaphoric aspects. This, as you would know, is one of the images which represents the Hindu lord of dance, Shiva Nataraja. And it's, of course, found in many museums and so on. And it had first came, I suppose, to global renown through the writings of Ananda Kumaraswamy in 1912, who described the image as poetry, but nonetheless science. And that was also because he was, of course, very inspired by the translations of the 13th century Tamil text Unmai Vilakam, which describes the imagery of the bronze as depicting the balance of Srishti or creation, which is depicted by the drum, and Samhara as destruction, which is depicted by the flame, which is held in opposite hands. And of course, you would also have been seen many dances and so on, which evokes, the Tandava, Ananda Tandava, and so on. And of course, I had been involved in the spectrochemical analysis of the image. And there we used the technique of taking a very, very tiny micro drilling using, you know, very fine drill bits of tungsten carbide, which is a very hard material, and then analyzing it using, in this case, inductive decoupled plasma optical emission spectroscopy. And then again, it was found to be a leaded bronze, 8% tin and 8% lead. But of course, as we know, this image has also evoked a lot of international interest, and following the writings of Ananda Kumaraswamy, there were other scientists who were also drawn to the philosophical implications. And in fact, Fritjof Capra, who was quantum physicist, but then he also was a popular writer. And he, of course, it's a very imaginative metaphor, but we shouldn't read too much into it because there's no real comparison between modern physics and all that with, you know, writings in ancient treatises, except for the fact that we can regard them as metaphors in that sense. And here he talks about, you know, how the dance of Shiva Nataraja evokes the dance of subatomic particles and so on. And Carl Sagan, of course, phrases it in a more elegant way, the astrophysicist, where he suggests that the imagery holds out a premonition of modern astronomical ideas. So certainly what he's trying to convey is that there seems to have been some sense of this balancing of forces of creation and destruction and all that, which does resonate with the way we see modern astronomy. And in that sense, I think more than other pre-modern traditions, I think this whole, you know, the Hindu mythology did encapsulate some sense of understanding, you know, the notion of, you know, balancing creation and destruction and so on, which and the long cosmic cycles and so on. So certainly in that sense, what Sagan says is as I think, a fair way of putting it. And so, but to me, apart from that metaphoric cosmic dance, so to speak, because, you know, even you have the metaphor of the Panchadhatu, or the 5 elements, which is associated with the dance of Shiva Nataraja, where, you know, he's equated with the 5 elements of earth, wind, water, fire, and ether. But I was, again, very interested in analyzing the actual physical elements of the composition of the bronzes, also because now these bronzes are, one problem is that we are not always able to date bronzes because they are made over so many, you know, hundreds of years, starting from, you know, the early historic and going into the later medieval. So quite often it's very difficult to actually make stylistic attributions and date them because all of the bronzes don't have, let's say, inscriptions. Some of the Buddhist and Jain bronzes do have inscriptions, but especially Hindu bronzes, which were basically, you know, supposed to be deities, they're not always inscribed, so it's quite difficult to make attributions. So among the scientific techniques which we can use for characterization and for provenance determination refers to the identification of the source of an artifact. Some of the useful techniques include lead isotope ratio analysis. And why lead isotope ratio analysis is useful is because the ratios of the isotopes of lead, Pb204, Pb206, Pb207, and Pb208 in a lead ore specimen will depend on the geological age of the deposition of the ore and the uranium and thorium geochemistry. And here I agree that I was quite inspired by my father, who was working, as I said, with nuclear fission and so on. And so you can use the lead isotope ratios to identify the source from which a metal artifact, the lead in a metal artifact can come, because different ore deposits have very discrete and measurably different lead isotope ratios. So anyway, for want of time, I won't go too much into it, but to explain the implications. So basically, as you see here, we've tried to plot some of the lead isotope ratios of artifacts and some of the ore deposits. And of course, we need to have the lead isotope ratios of an ore deposit concretely to be able to find an artifact that's matching it. And sometimes we don't have the full data of lead isotope ratios for ore deposits. But where we do, we can find some matches. For example, this is a very beautiful Jain image of a Tirthankara, which is inscribed to the 12th century. And it is, again, from the Solanki or Chalukyan dynasty. And in this case, it's a brass image. I've been talking about bronze so far, but this is a brass image. As you know, brass refers to an alloy of copper with zinc, whereas bronze was referring to copper alloyed with tin. And this is a brass image with about 24% zinc. and it matched this polymetallic deposit here of Ambaji in Gujarat. So if we know the lead isotope ratios, we can technically actually make some pretty good matches. So we can say that yes, this fits the fact that it comes from Gujarat and so on, and those kinds of things. But what is quite interesting is sometimes you find an image, like this is an image of Buddha from Kanchipuram in Tamil Nadu, which exactly matched also the lead isotope ratios of this Ambaji mine. And this is also brass of 21% zinc. So we can say that it seems likely that this metal actually came all the way from Gujarat to make this metal artifact. So it gives you some idea of trade and exchanges and so on. And similarly, some Shatavahana coins from the Andhra region. I had shown you that Agni Gundala mine right in the beginning of my talk. And so the lead isotope ratios for this silver coins, because silver also has a lot of lead, because silver deposits and lead deposits are all sometimes polymetallic, and the galena occurs along with silver deposits and so on. And here we found that the lead isotope ratios matched Agni Gundala. So some lead was coming from Agni Gundala for the Shatavahana period, which is about 1st, 2nd century. But some of the lead was also coming from Fluminense in Sardinia. You can see here, this is Fluminense here, and this is Agni Gundala here. So there are two different sources. So there's also long distance exchange, and we know in the early centuries CE, there was Roman interaction and so on, and trade going back and forth with the Roman world. So now I think I'm running out of time a bit, so I'll have to rush through some of this, but this is also to point to the composition and analysis of the bronzes, which I had done using inductively coupled plasma optical emission spectroscopy. And of course here, this is also to tell you that these bronzes were made by the solid casting process, where a solid wax model was made and then invested with numerous layers of clay. And you can use a technique of radiography also to, it's just exactly the same principle as X-ray of your lungs or whatever. And you can see that it's totally dense because it's a fully of metal and so on. So this is how you can use other kinds of diagnostic techniques. And of course, I'll pass through this. You all can always look at the papers for the technical aspects. But now coming to the other implications, one of the interesting aspects was that even though we may not always be able to identify the ore sources because we may not have the lead isotope ratio data of all the ore sources, we can find this kind of clustering associated with different stylistic periods of bronze casting, which suggests that the similar ore sources were being used at different periods. For instance, the Chola bronzes are clustering here, which is dated to about the 10th, 11th century, and the Vijayanagara bronzes of about the 14th to 16th centuries are clustering in a different region of the lead isotope ratio plots. So that can help in telling apart bronzes. So using that, I was able to actually redate some of the pieces which we could not actually make the attributions. This is a very typical Vijayanagara style piece. And you can see that the Vijayanagara style, we always say that the Chola and maybe even the Pallava period had show greater finesse maybe in the bronze casting, and this is the later period. But one very interesting finding, and this is of course a Nataraja piece of the Chola period here, which fitted that particular ellipse and so on. But one very interesting finding was that already by the Pallava period, the Nataraja bronzes had been cast. And this is something that from stylistic study, nobody had actually written about that because it hadn't been detected from just stylistic analysis, because you can just see that and say, oh, well, it doesn't look very different from Chola, so it could just be Chola. And it was generally assumed that the Nataraja bronze was not cast before the Chola period. But clearly, this is a Pallava example, and we see it also fits quite closely with the Pallava sculptural style here. So this is how you can help to redate images using scientific techniques, which you can't do just from art historical or visual inspection. And since we're talking also about physics here, one of the interesting aspects of the study that I had made was also, this was along with an astrophysicist, where there is an interesting tradition, this is also looking at the intangible cultural heritage, that in the Chidambaram temple in the coast of Tamil Nadu, you have a tradition where the Nataraja image is worshipped in the month of December. It is known as Arudra Darshanam, where basically the constellation of Orion appears right up at the zenith. If you go to Chidambaram at that time of the year, you'll see, and the star Betelgeuse is right up there in this night sky. And this is referred to as Arudra Darshanam. And so it seems that this, and Arudra is referred to as a star associated with the Shiva Nataraja or Rudra. And those are nuances which also go back to Vedic writing and so on. So it seems that, this was a way of also venerating. I mean, in those days, this happened in various cultures. The Greeks also, looked at Orion and, described it as a hunter and so on. So something similar here where, it seems that the iconography of Shiva Nataraja may have also been, to some extent, inspired by the observation of the constellation Orion, and we had done this star chart plotting. And one of the interesting aspects is that the leg of Shiva Nataraja, which is very distinctive iconography that you see in the Tamil tradition, the leg extended like that, to form this Ananda Tandava depiction. It seems that that leg seems to point towards the star Sirius, which is also known as Mrigavyadha. So it seems that this iconography could have inspired the depiction of this image. And there was also a Tamil book, which was, of course, of the early 20th century, where there is some of the Dikshitas or the priests mention this depiction of the Arudra Tandava of the stars of, the Orion constellation forming a kind of wireframe. And the late Ganapati Stapati had also said that this, he was a sculptor from Mahabalipuram who had said that this was, also an underlying aspect of the iconography. So you can see how the stars also inspired iconography. Now I'll very quickly go to the topic of, I have about 15 minutes. Very important topic of iron and steel. And of course, this is the very spectacular and famous Gupta era Delhi iron pillar of 400 CE, which is in the Qutub Minar complex. And there is an inscription which suggests that it was made in the Gupta period around 400 CE. There's a Gupta Brahmi inscription, of course, in Sanskrit. And what is interesting here is that this is the SEM analysis, and of course we know that it's been hailed as the rustless wonder because it hasn't rusted very much. So there's been a lot of studies, and it's been suggested that, of course, apart from the humidity, very low relative humidity of Delhi and so on, one of the reasons for the rust-free aspect is that it contains some traces of phosphorus, and that leads to some segregation to the surface, forming a passive protective layer, which has prevented it from rusting too much. And of course, this is made by the process of forging wrought iron, forging various cakes of wrought iron and then piling it up one on top of the other. Now, of course, iron, I think, as you may be knowing, there is the Copper Age and then the Bronze Age, and before that the Stone Age, and the Iron Age, which comes into vogue around 1500 CE in different parts of the world. Though, of course, now we're getting very early dates from India and also from Tamil Nadu, going back to 2000 BC, which seem to be some of the earliest, Mailadum Parai, but I don't have time to go into that. So here you can also see some of the slag entrapment in this microstructure. And of course, the phosphorus, it would have also been, and the enrichment would have been an aspect of the primitive, in this case, process of, making of iron, which is smelting of iron, using these shaft furnaces. And it's basically a solid state reduction, whereas for the copper extraction, the copper ore actually goes into the liquidus and then it is smelted. But it is a solid state extraction here, which of course I don't have too much time to go into here. But the traditional communities which did the iron smelting were the Agarias. And you can see here the lady here with this is from central India and Jharkhand and so on, and the woman working the bellows here. And the process really involved a process of continuous feeding of charcoal as fuel from the top of the furnace. So we try to replicate here, we try to do experimental smelting here in Nias to do this kind of iron smelting to understand the nuances. And believe me, it's difficult. It's not as trivial as it seems. You get greater respect for the traditional aspects when you actually try to replicate it. Now, I was talking about wrought iron, and you see here the phase diagram, the iron-carbon system with what happens when you keep adding carbon. Now, in this case, it's an interesting, we talked about bronze, which is basically alloy of transition metal elements. But here we're talking about the alloying of carbon, which is basically, carbon, of course, has many allotropes, but is also, it is both organic and inorganic. Inorganic when it's diamond and so on, but it's organic as carbon from the atmosphere and so on, and carbon monoxide, carbon dioxide and so on. In this case, it's carbon which is alloyed to iron, which causes very interesting properties. And wrought iron had very little carbon, less than about 0.04% carbon. But then now we come to a very interesting tradition that was well known, particularly in South India, for making what is called woods, which is a type of steel which had about 1.5% carbon, around this range. And of course, cast iron, which was made mostly in China, had about 4% carbon, but we are talking here about woods which had about 1.5% carbon. And what is interesting is that woods was a novelty because it was not very well known in Europe, and it was exported from ports in South India and all that we know, especially to West Asia and the Arab world and the Persian world, to make these very spectacular blades known as the Damascus steel blades. And what was famous about these Damascus blades is that it was the forging of this wood ingot which gave these alternate patterns of light perlite and which is dark, the perlite is dark and the cementite is light. So these wavy patterns, which was known as damashq in Arabic, which basically is compared to silk also, the patterns in silk and so on. And these sword blades had very good properties. Of course, they're also made in India, the armory here and so on, whether it's Nizam or Rajput and Mughal and so on. But they were also especially sought after in the Arab and Persian world, which made very good swords. And now what is interesting is that this term woods itself refers to, it's derived from the Tamil word ukku or urukku, which refers to the process of melting. So here what was happening is that the wrought iron was being carburized in crucibles so that it reached the liquidus really. So at very highly reducing conditions, the liquidus is reached here. And in this viscous condition, the wrought iron was being packed with very carbonaceous materials like leaves and wood and so on. And through that, the wrought iron was being carburized to give high carbon steel here. And this is typically the microstructure that you see. And it basically, austenite here has this kind of hexagonal structure. So it's the prior austenite structure from which, when it has come down from slow cooling, you see here the cementite needles here and the prior, the perlite, which is within cementite. And this perlite surrounded by light cementite is what, when it's forged, it gives this typical composition of wood steel. And here you also see, of course, these are some very fine spears and so on from Adichanallur. And as I was mentioning, the Sangam text, the poetess Avayar also in about the 3rd century BC to 3rd century CE, she writes of a lot of these poems to do with the term yegu is mentioned, which could also be derived from woods. And it's interesting that Zosimus the Greek in the 4th century also mentions that Indians fused iron in crucibles to make weapons. And why this is important is because in the Western world, it was the solid state cementation, where if you basically heat, you might have watched your blacksmith doing it, he'll heat the blade in fire. And that does cause a little bit of carbon to go in, but not a lot. So that's why it remains low carbon steel. But the use of high carbon steel is something which was really mastered in, it seems now with more and more evidence, particularly in South India. And here, this is a crucible fragment also from the site of Kodumanal. And here you're seeing, this is, Kodumanal was also associated with the Tamil Sangam literature because it's mentioned as a Chera capital and in the Sangam Tamil literature. And this is important also because, by this time you have also a lot of evidence of Indo-Roman trade and so on in South India and Karur. And this is a beautiful gold signet ring which shows that it is of an Indo-Roman type because it's a signet ring in the Roman style, but it also has a very typical Indian theme of the Mithuna couple and so on. And you see that the Roman accounts also talk about iron from the Ceres. And this Ceres might refer to the Chera kingdom of this domain, of which Kodumanal is a capital. And this is in fact a cross-section of the crucible, which one had done metallography, and then looking at the other techniques, here what was used is scanning electron microscopy with electron probe microanalysis. And this is a dot matrix map where basically you can map the concentration of elements across the surface. And this shows, the enrichment that you see here, the iron in the crucible matrix. So this was you can tell that this was actually used for crucible processing of iron. So this is how the analytical techniques can use to tell us something. And this is a microstructure of a nail from Putnam. And what is interesting is that it has exactly the same structure that you saw in the, this is from the crucible fragment from Mailsirivallur, where you can see that the droplets of, the remnant droplets of Woods are formed here, the hypereutectoid steel, the pearlite surrounded by cementite. And that is exactly what you're seeing here. So basically it confirms that the crucible processes were being used to make this high carbon steel, which, this is how we reconstruct from archaeology, the findings of the past. And because we really didn't know how far back they were making this kind of crucible steel, which had been observed by European travelers, but now we can say that this definitely goes back to the Iron Age, early historic, from these kinds of finds. And again, to show you some of the examples, this is actually a toddy tapper's knife. Even until recently, it was being used in Nizamabad. And you see here, again, through SEM analysis, the pearlite and the cementite matrix. And this is a very beautiful blade of the Tipu Sultan era. And this, of course, follows another kind of technique, which is known as the Koftgari work, which is gold damascening and so on. And this blade also has this Damask pattern and such like. And this is a painting of the Nizam era and so on. And of course, what was interesting was also this particular type of steel known as ultra high carbon steel with about 1.5 to 1.8% carbon steel was also patented in the early 80s, because they found that Sherby and so on found that this is a material which we can term as superplastic, which means that it's highly formable at high temperatures. And here you can see what happens with the strain rate, that there's at high temperatures highly formable, and that is what this graph shows you here. And then it was found that actually this ultra high carbon steel composition really matches this wood steel. So we can say that already in antiquity, something which has been patented had been being made over centuries. And as you can see here, this honeycomb structure, what happens here is that as you forge that ultra high carbon steel at high temperatures, it becomes spheroidized. The cementite becomes increasingly spheroidized, and that's why it becomes super formable. So it also explains to you how they would have forged these blades, because it was not forged at red heat so much at this temperature where it becomes superplastic. And that's also interesting because many of the Europeans who actually took back these ingots in the 18th century, they actually couldn't forge this wood steel. And in fact, Romer said that he couldn't find any blacksmith in Paris who could forge these blades, because it was a very special skill that had been developed in Asian antiquity to forge these blades. And again, the microstructure. Now, one more area of interest has been in the aspect of nanomaterials. And in fact, Reibold and all have suggested that when you resolve the structures of some of the blades, you see the formation of nano-wide cementite and carbon nanotubes and so on. So these are now the new areas of interest in some of these ancient materials, that we're actually finding that these are nanomaterials. And you would have probably already had some talks on nanomaterials and nanotechnology. Famously, Richard Feynman, in his classic lecture of 1959, wrote that there is plenty of room at the bottom, and that atoms on a small scale behave like nothing on a large scale, for they satisfy the laws of quantum mechanics. So as we go down and fiddle around with the atoms down there, we're working with different laws, and we can expect to do different things. Of course, that was quite prescient in the late 50s, and now there's been so much more work. But speaking of the carbon nanotubes, so you see here that this is made of carbon with a diameter of the nanometer range, and of course, they are allotropes of carbon. And what is also interesting, of course, they are members of the fullerene family, which had been first discovered in 1985. And that's when the carbon nanotubes came to public awareness, and they were produced by laser ablation and so on. And what is very interesting, of course, is that these are very robust and difficult to break, and they are light. And in fact, the strength, when we're talking about steel, is it's supposed to be almost 100 times stronger and so on than steel. So there's a lot of interest, of course, in the carbon nanotubes. though we still have to do some more work in terms of the integration into the steel matrix and all. But it's quite exciting that also in the ancient materials, you're finding very advanced materials. Of course, these were accidentally made. They didn't know the science of it. So it doesn't mean that they knew what they were doing. It's just that empirically they've arrived at a material. And today, we are, with all our modern science, we're able to find that, oh, these were actually quite sophisticated things going on, which was done in those days empirically. So we shouldn't, it's wrong to say that they already knew nanomaterials. That's not right. It's that the nanomaterials can also be found in ancient materials. And this is, of course, a crucible which for the steel making, which we had then, you can, again, looking at the other kinds of investigations, this is a CT scan which shows the different layers. The carbon-rich layer here, which was used to carburize the wrought iron to high-carbon steel. And the outer layer, of course, was made much more refractory. It was deliberately being packed with quartz and other very refractory materials so that it could withstand very high temperatures, because it had to withstand very highly reducing conditions of about 1200 to 1300 degrees centigrade. As I said, the reason that, you know, iron metallurgy developed later was because it needed very highly reducing conditions and temperatures. So that's why it also was discovered much later. And here you see the fabric of the crucible on which we have done scanning electron microscopy. And it's quite interesting. Of course, these are the metallic remnants of the iron, and then there's a glassy matrix here and so on. And you're also seeing here that they were deliberately adding these rice hull relics into the matrix of the crucible, especially this layer, which needs to be very carbon rich. And that's interesting because the rice hull relics, when they are cooked, you know, they become very rich in silicon. And in fact, I found some formation of silicon carbide as well in the rice hull relics, which is also very good refractory. So it points to how this would have helped in carburizing as well as creating a good refractory material, again, using traditional materials. And other scholars have also found the formation of mullite networks and so on. And another interesting aspect is that I found that there are quite a few specks of zirconium-rich materials through the fabric. And of course, we know that quartz was being deliberately added because quartz is silica-rich and it's quite refractory. But this findings of zircon minerals and tiny specks, because some of the sands in Andhra Pradesh apparently are rich in zirconium minerals. So that could have also contributed to improving the refractory properties, because zirconium is also one of the highly refractory materials which are used in modern conditions. So even in the traditional setting, some of these were, you know, being used. Of course, they would have sought out the materials that worked for them, of course, not knowing exactly what they were and so on. And another interesting aspect, because I would like to, of course, keep the emphasis on women, I was quite struck by, if you'll have been to Kerala, you know, the Kalari Paitu tradition, where you have this blade which coils up like that and then it uncoils, and so you can use it. You know, it's quite, you know, swashbuckling to watch, and this is a practitioner here. And I found that this is quite interesting because it's actually made of spring steel, which had about 0.8% carbon in it. So not all the steels that we're using, they had some specific kinds of steels that they were using for specific purposes. And here, this is what we call spring steel. And we know that spring steel, of course, came into vogue in Europe for clock manufacture and so on by the 15th century. But here is an example of use of spring steel, of course, in a different context, maybe less functional. Now, I think I just have another 2-3 more slides before I finish. But I should say that the whole research in woods, because there was so much fascination in the 19th century, 18th, 19th century with European travelers, like, you know, taking back the ingots and trying to study them, because they were, this wood steel also had very good cutting edge and properties of cutting and so on, which is why it was investigated a lot. And it also inspired Faraday to, towards his work on alloy steels. And of course, empirically, woods was being produced in India and so on, but the science of it, we were not, of course, concerned that much with trying to understand the science of it, and we should really grant it to the Europeans here. For instance, Briand here in 1821 did 300 experiments to understand the composition of wood steel. And he also tried to, you know, alloy iron with uranium and palladium, because what was not understood is that it was actually carbon which was causing the properties of steel. Nobody could really figure that out. And then it was in 1825 that Mushed recognized that the Indian process amounted to the action of carbureted hydrogen gas in converting iron to steel, and then he took out a patent. But okay, we may grumble about that, but he did try and understand the science of it, so fair enough. And also in Tobin Bergman in 1781 studied the various compositions of cast iron and steel. And he also had suggested that it was this black material called carbon, which was behind all this, though he called it plumbago in those days. Of course, in India, you do have some of these blacksmiths, but unfortunately, most of them have no memories now, and the tradition has been lost in India. That's also very sad. But speaking of carbon, and because, I was also, with respect to a talk I gave for the carbon exhibition, the carbon we know in that very black form that you saw, lamp black and so on, but it was also an allotrope. You have the spectacular diamond, which is an allotrope of carbon, which, and in fact, India has also been the source of early diamonds, because one of the most famous sources of diamonds is Golconda in the Andhra region. And it's interesting that we also have some of very early evidence that diamond drilling was used, because we know that diamond is very hard. The hardness of quartz is around 7, and diamond is the hardest at about 10. And here you have these quartz beads from this megalithic site, Kodumanal, which I talked about, where we could find some wood steel crucibles, 5th century BC. And this is, in fact, one of the cyst burials here at Kodumanal, which typical menhirs and so on, and the quartz beads which are found. And it is suggested that they would have had to have used diamonds for drilling, because there's a technique of using diamond bow drills, which was also used in Karur, but also in Cambay, if you go in Gujarat, going back to earlier times and so on, because that's how maybe some of the lapidary work going back to Harappan times was done, by using this bow drill, which had a tip of diamond, and then this was moved back and forth and so on. So, and then so that this drill would have gone through, and the bead would have been kept here and so on. And some spectacular, of course, gold jewelry, temple jewelry with the Naga motifs and such like. And of course, speaking of carbon, this was one of the materials actually, which again, as I said, being an organic material, it was really Antoine Lavoisier in 1772 who showed that diamond was a form of carbon, and he did a very spectacular experiment, and known as the father of modern chemistry, where he actually took a diamond and burnt it in using sun rays in a jar to show that the diamond disappeared as carbon, and then he weighed it and showed that it had the same weight as after it was burnt, and then he bubbled the carbon through lime water to get calcium hydroxide, confirming that the diamond had burnt down. And so even today, I mean, jewelers have to be very careful when they are setting diamonds in the kundan and so on, if they do it on the base metal, that they should not burn it down if they use a blowtorch. And of course, we should also make a mention, since we of our own, especially Bangalore's own Nobel laureate C.V. Raman, who received the Nobel Prize. And if you'll have time to also go and see the Raman Museum, please try to, in the RRI and so on, and who received the Nobel Prize in 1930. But he also studied the diamond crystal lattices and the different monochromatic frequencies and so on. And of course, this is also the spectacular Kohinoor diamond, which is part of the crown jewels of the in UK, in the Tower of London. And that is also said to have been taken away by Nadir Shah. It was on the Mughal peacock throne. And according to legend, it was also part of the eye of the goddess Bhadrakali of the Kakatiyas of Warangal, the icon of Bhadrakali, and was mined from the Golconda mines in Telangana. And lastly, of course, since we're also in Karnataka, I should make the mention of another important case of transfer of technology, because as we saw, the case of making high-grade crucible steel was patented by the British based on the process that they observed of crucible carburization. Visitors like Buchanan and Voici and so on observed the making of wood, steel, and so on, and that was actually patented there. So it was a clear case of a transfer of technology. We have another very interesting example of transfer of technology from east to west of the ferrous metal-cased rockets of the 18th century in Mysore, and these are these Tipu era metal-cased rockets in the Shimoga Museum. And so we know that in the Battle of Poliur against the British in 1780, Tipu is said to have used these rockets, and also in the Battle of Seringapatnam or Srirangapatna, where these rockets could, in fact, said to have been able to kill about 3 men. And basically what it is that you had a metal casing here, and of course attached to a long bamboo stick, and this contained the charge, which of course consisted of sulfur and gunpowder and saltpeter and so on. And apparently it could also, wreak quite a bit of harm on the people here. And they sometimes also had some kind of weapon, like a knife attached to it and so on. And so if you all have been to Srirangapatna, you'll see the Darya Daulat Bagh Palace there, and also some of the murals which depict the Battle of Poliur and so on. And so the technique we used here was spark source mass spectroscopy. And what is also interesting is that how in that time they were already able to make these very fine rolled casings of mild steel. The composition here of 0.2% carbon is more what we call mild steel. And so this is again not known how quite early on they were making these, rolled mild steel casings, and then of course a propellant and such like. And then it was William Congreve who, after the Battle of Seringapatna, had taken some of these rockets. I mean, not William Congreve himself, but the British who had taken some of these rockets to the British Arsenal, Royal British Arsenal, and then it was studied by William Congreve, who is credited with the modern invention of the rocket. So you can see here that this was a case of inspiring, of course, now it's gone to very great advances, the rocket technology, but we can see here the seeds of inspiration from the Indian process. And speaking of women, we also know that there are several women scientists in ISRO from around India who've made great pioneering contributions to satellite and space explorations. So here's to all of you women in physics, and I wish you all the very best to, soar and reach great heights. And thank you all for your patience.
Questions? Anyone? So I'm a little lost here just about this, please correct me if I'm wrong. So as far as I know, the Damascus pattern is from the Damascus steel is made by forging it, whereas Wood's metal, it can't be forged. Is that right?
Yeah, well, the ingot, let me just go back to that. Sorry, the ingot is then forged, right? So this is the ingot over there, right? This is what it looks like after it is, this is the crucible. And after the wrought iron has been carburized and so on, this is what it looks like. And in fact, it was described as a cake. And this is actually what you would say it's a cast steel. The structure is more, let's say, dendritic and so on. So then it is forged. But the point is that the forging of this is quite difficult because, as you know, cast iron becomes very brittle. So cast iron is not a good material for forging. So when you look at beams and so on, it's more of lower carbon steel, because with that 4% carbon in cast iron becomes brittle. And woods is also slightly brittle, but there is a way in which it can be forged at a particular temperature where, it's in the superplastic range, yeah, which is somewhere in this sort of temperature range. So that there was a certain skill that the blacksmith had to have. And, this is still, we don't quite understand what they did to reduce that brittleness and then forge it, because this is where the European blacksmiths found that they weren't very able to forge it. And so there were some skills that the Indian and Asian blacksmiths had, or the, Middle Eastern blacksmiths and all that had developed in terms of forging that ingot and, reducing the brittleness. But also I think it would have been in terms of, not going to white heat, but where it is slightly below, where that superplastic temperature range is achieved. But we still don't quite understand how some of these nuances, that's where we need to do more of the studies. And that is where the spheroidization, the temperature at which UHC gets spheroidized is important, yeah? This, where it sort of becomes spheroidized. This is important to understand. But I think we need, see, one problem is we don't get too much of samples of archaeological material to study because museums don't want us to give, don't want to give all these things. I mean, in the earlier days, I could take very small specimens for metallographic analysis and things like that. And here, for instance, this is a blade which shows you the edge has been spheroidized here. But lately, it's very difficult. And okay, XRF, they're happy for us to do, but it's just a non-destructive analysis on the surface. You know, we need to look at the microstructure to really analyze. So there are a lot of these challenges, but anyway, we still try to kind of piece together as much as we can.
Do you think maybe they would have been a way they were able to achieve that just by melting or like the malleable properties or something like that? Is it
Just
possible?
by melting, because the thing is that it is a very high melting, alloy. So if your blade totally melts, then that's no good either. It's at that superplastic range where it is just whisk. You know, if you watched a blacksmith at work, he does that in a certain kind of flame, and he knows where it becomes just kind of viscous enough to be able to hammer. Actually, even just by putting a blade in the flame, it gets carburized. So actually, he would have started out with just low carbon raw iron, 0.04 carbon. And then when he puts it in the fire, some carbon gets in. So then it becomes, let's say, 0.1% carbon. It actually becomes steel. And that's why he can't, you'll find when the blade goes blunt, you can't use it. But then the minute he puts it in the flame and then he sort of hammers it, what he's doing is actually carburizing it so that it becomes more like steel, and then it's more ductile, right? It can be forged better, and it can also, the cutting edge and all that improves because he's able to get a very fine cutting edge. Yeah. So, but there are many nuances to this. For instance, the Japanese discovered a completely different way in which they forged low carbon iron and high carbon iron, alternate like layers of low carbon iron, high carbon iron. That is a katana sword, it's called the samurai sword, where manually here the ingot itself had low carbon perlite and high carbon cementite. So you just have to forge the ingot and you get that spheroidization taking place. But there they were literally taking, iron of a low carbon content and high carbon content, because in their furnace they were using a different way of making a steel, which is called the Tatara furnace. So from the Tatara furnace you could get steel which was low grade and high grade, and of course they had some ways to figure out the two grades, and so they were hammering alternate layers so that manually you were getting a structure of alternating light and dark patterns. So there's a lot of different things, how different cultures arrive at similar structures in a way using different techniques.
Any other? Yeah.
Ma'am, could you like elaborate on trace element analysis and which elements we can actually detect using it?
Yeah, let me go back to, yeah. So, well, it depends very much on an analytical technique you're using. If you're using, let's say, atomic absorption spectroscopy, which is you do serially, you have to analyze element by element. And in fact, in my early times, that's what was available. So you take each element and then you have to get the flame for that particular element, flame atomic absorption spectroscopy, and that particular. So it's a serial kind of analytical technique. These days, of course, it has moved to different kinds, like mass spectroscopy. The advantage is that you can analyze a whole range of elements. And what in those days we were using was inductively coupled plasma, atomic optical emission spectroscopy. But also, like with mass spectroscopy, you can analyze like a whole range of elements, 18 elements or something. So you get the entire range. And nowadays, you also have, of course, the laser ablation mass spectroscopy, because in those days, we had to take micro drillings and then make it into solution for the mass spectroscope. It has to go in as a solution. But now you can also, laser ablation means you can just take a bit of the solid metal and, it gets ablated so that you get the complete spectrum and so on. So, of course, depends on the sophistication of the techniques. And of course, as I said, these are basically copper alloys. So in that case, you'll get the major elements, the minor elements, and the trace elements. So the major element in this case is copper. The minor elements are like, let's say, tin or lead or zinc or whatever. Yeah, mainly these are the three minor elements. And the trace are whatever you get, which is less than 1%. But the trace elements are actually quite interesting and important also, as I found in my studies, because there are some trace elements which are what we call chalcophilic, which means that they tend to segregate with the copper ore, because when the copper ore itself has some elements which are characteristic of that copper ore. Sometimes it can be rare earth metals also, like say selenium or something like that. But so those chalcophilic elements tend to segregate also after the smelting process. It's there in the final metal. It's not necessarily the case, but it can be the case. And what I actually found is that some of the chalcophilic metal elements here, like nickel, cobalt, nickel and cobalt particularly are very, um, they tend to reflect the ore source. Nickel, cobalt, arsenic, antimony, and bismuth. These are what we call the chalcophilic elements. I mean, iron is not a very typical element because iron can vary very randomly, because iron can also come in from some iron ore, which, because sometimes you get chalcopyrites, you get associated iron ores, it can come from flux, it can come from a range of sources. So iron is not what we call chalcophilic, but these other elements are. And what I actually found, and so are actually gold and silver are also chalcophilic. But you see, in the case of the South Indian bronzes, so actually what I found is there was some patterning based on the chalcophilic elements based on the ore sources. So there was some clustering across different groups of bronzes of different periods, which came from different ore sources, which also was reflected in the clustering of the trace elements, which in a way I could also use to tell apart bronzes of different periods. But it's also interesting that actually the gold-silver ratios also should show linearity, which reflects this pattern of being, related to the ore sources, being chalcophilic. That should be normally the case. But in my South Indian bronzes, the gold-silver ratios were all over the place. And the reason for that's a very interesting reason. Because although these are copper alloys, I mean, often when you go to the stapatis and all, they call these bronzes panchaloha, which means 5 metal icons. And nowadays, people totally mistake it to think that it is 5 metals or 8 metals in all different, in major element portions. But you can't actually have alloys with 5 to 8 elements. You can't, the phase diagram won't permit you to make it. But what was actually going on here is that, what the Sapati explained to me, that as a Shastra, they sometimes add very small amounts, like a tola or two of gold and silver, which is more like a Shastra, that it contributes to the auspiciousness of the image, it makes it more auspicious and all that. So the fact that the gold silver didn't show any kind of linearity or any kind of, kind of clustering like the other trace elements suggests that they were adding these minor amounts of gold and silver just as a Shastra, because that was a practice. And in fact, if you ask him to make a Panchaloha icon, you can just buy from the goldsmith very small amount and just add it, like he will add it as a pinch in the casting, the final, with a spoon, he will add it just to the final stage of the casting. But it won't reflect in the composition more than 1%, because these are very heavy metal castings, like like at least 50 kg to 200 kg. So even if you add like 1 tola or something, it won't be detected in any significant way above 1%. So that was explaining why I was not getting a clustering with the gold-silver composition. Although, mind you, people who have done studies on, say, Mediterranean bronzes and all, they have found that gold-silver also is a good, the gold-silver ratios also show some trends for some bronzes from sources. So it can be chalcophilic. But in my case, this could be the explanation. So this is how we use analysis in a range of ways to kind of, along with the understanding of the archaeological context and the actual practices that were going on, the ethnoarchaeology, to come together to make inferences. So
let's thank Professor Sharada.
Thank you so much.